and away. The city, a vast repository of stories, each one branching out like the threads of complex code. They say every commit tells a story. So, what's my story? Failed developer turned cop? Couldn't write code, so decided to pick holes in others? Maybe it's me. Maybe I'm the issue in this repository. All I know is I'm the city's most trusted investigator. Lately, something's changed. Whispers say there's a new kingpin in town, pulling all the strings from the shadows. Goes by KB. Whoever it is, they are the kind of criminal that doesn't leave fingerprints on the keyboard, just a trail of cryptic commit messages and coerced histories. Anyway, this city is my home directory, and I'm here to clean up the code smells and corrupt blobs. No matter how many conflicts I have to resolve. Welcome, ladies and gentlemen, to Crime Scene Investigitor, the case of the naughty commit. Welcome, cadets, to your very first day of Detective Academy. Now, you've all just graduated from basic police training and you think you're hotshots, but you're in my house now. Who am I? I, of course, am Chief Inspector Detective Kadel, and I will be your teacher on these first few days of Detective Academy. I, of course, am a principal platform engineer for Android at a company called Babel. And when I'm not Androiding or platforming, I love the terminal, Bash, and got really obsessed with Git. Now, if you enjoy any of the nonsense you see here today, then selfish plug, I have my very own stupid YouTube channel, so if you want more ridiculous bullshit in your face, check that out. Now, because it's your first day of Detective Academy, we have a jam-packed session. To start with, we're going to make sure we're all on the same page with the basics, the internals of Git. Then, excitingly, we're going to take you to a mock, fake crime scene where we've set it all up so that you can investigate your first crimes and bring a perpetrator to justice. Now, everything you see here today in Detective Academy has been very well documented in this Linktree link here. You'll see it throughout the day, slides, and all of the videos, articles, and whatnot I link to can be found there. And also, you are welcome to take photographic evidence. Just make sure to capture my good side. But please don't panic in case you miss something on the slides, because the slides themselves are included in the Linktree. Now, very important, before we set off today, I need to introduce you to somebody very important to me. My detective partner of many years, Detective Refi.
Hey, nice to meet you, folks.
Refi is a marvelous sidekick. He is the Batman to my Robin, the Robin to my Batman.
Despite what this guy says, I'm the real brains of this duo. Somebody's got to keep Detective Kadel from walking into open manholes.
Hey, Refi, excuse me, we said we wouldn't discuss that in front of the cadets. Anyway, okay, Refi is a wonderful partner, and we can trust him entirely. Anyway, the last note is that the work of an investigator is not about assigning blame to an individual person. No, it's about having the skills and the ability in Git that when a problem occurs in your repository, that you can quickly, easily solve it and be the hero your team needs. Now let's dive in. Spin move, thank you. Git, of course, is a version control system, meaning that it tracks changes to your repository over time, blah, 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 blah. It stores these moments, these snapshots of history in these things called commits, and they're always signified by these circles in these diagrams. Boring. Each commit has a unique ID that's actually a 40-character-long SHA-1 hash generated from the contents of the commit itself. Cool. So commits have IDs. Commits also have a reference to their parent commit, or the commit that came just before them. So in this case, C knows about its parent B, but B doesn't know about its child that it abandoned when it went to get cigarettes that one time. And this creates something called a DAG, or a directed acyclical graph. It's just a fancy way of basically saying you can pick any moment in time and through the lineage find your way back to the start of history. So every commit has an ID, every commit has a parent reference, and hopefully somewhat obviously, merge commits have two parents, right? Right, good, detectives. So we've learned about commit objects briefly, but there's two other types of objects that exist in Git to make Git do its gittiness. And these are called trees and blobs, and it's very easy to think about. Commits are the overarching containers of change, the punch in time. That's a commit. And inside of a commit contains everything else we need. In fact, a commit has a pointer to exactly one tree object. And tree objects can just be thought about as like the printouts of folder contents, like you've LS'd a folder. Cool. So there's tree objects, and tree objects can have other tree objects, aka subdirectories, and the final object type, which is blob objects, which you can basically think of as the contents of the files. And with this very simple three-object structure, Git is able to recreate our folder structure throughout history. But this is all very theoretical. Where are these things? Where are these objects stored? Can I touch them? No. Bad. Don't touch objects. But they are there. They are just files on your machines. They are located inside each and every one of your computers because of distributed version control. Inside the .git objects directory. And all of these different commit, tree, and blob objects are stored happily side by side there. Delicious. So they're files on your machine. Let's just take a quick sidestep. Thank you. And figure out how Git turns some of your code into some of these objects. Let's look at a blob object, for example. When you use the git add command, Git takes your plain text Cody file and first of all hashes the contents of it. That gives us that lovely SHA-1 hash. We'll put that to one side for now. Then Git takes the contents of the file and compresses it using zlib. Make it smaller, more efficient to store on disk. Nice. And finally, Git goes to that .git objects directory, takes the first two characters of the SHA-1 hash and makes a folder name out of it, if it doesn't already exist, makes a folder out of it. And then within that folder, it takes the compressed content and jams it into a new file, which it will name the 38 remaining characters from the SHA-1 hash. Well, that's weird. Detective Kadel, why is it doing that? That's weird. Well, this is one of Git's many efficiencies and why it is so goddamn popular and brilliant. Imagine a world where Git doesn't do this system, and all of the objects are just stored in one folder side by side. Hundreds, thousands, maybe millions of object files. Every time Git needs to do something Gitty, it needs to index through all of those files. Whereas here, with this approach, it needs to index through a maximum of 256 subdirectories, because of hex. And then some subset of files to index through. So it's an efficiency, and Git has lots of these little hidden wins. Now, these objects are files on a machine, so we can interrogate them, right? Being the experts that we are. We can maybe cat out the contents of these files. Well, no, it's compressed gobbledygook nonsense. But we as detectives need tools to be able to interrogate these objects, and we have such tools provided to us by none other than Git itself. And in this case, we're going to look at the Git command line interface. Now, raise your hands in the audience if you use Git from the terminal or the command line often. Excellent, good, yes. Those of you who raised your hands, fabulous, well done, 10 points. Those of you who didn't, please stay behind after class for a conversation. Anyway, no. The reason that we're going to look at these tools through the command line interface is because, one, that was how it was intended to be used by professionals. No, I'm just kidding. I'm such a bastard. Anyway, but the other side is to deeply learn the concepts the hard way, so that when you go back to your disgusting GUIs, your sours, your towers, your source trees, you'll at least know what's happening when you click that gross little button. Now, does anybody know how many Git commands there are in existence? Just yell numbers at me. Anyone? 300? Bit lower. 12? A couple more. 56? 200? It's close as one. Okay, so rip that Band-Aid off. There's 149 commands as of when I was making this presentation, and they can be split into two different categories. Porcelain commands. You can think of these as the friendly, user-facing commands that we use every day to interact with the Git system, like add, commit, and branch. And then there's plumbing commands. These are the dark, mysterious back-end commands that Git itself uses to do its gitting, and are really useful if ever you write scripts for Git. Just a sidebar. So we know there's objects. We know we have maybe some tools to interrogate them. Let's start learning about some of the tools. the command line gives us. Now, we can use git revlist with these flags to list out all of our objects in the repository. Hooray! Fine. Detective Kadel, you've done something silly there. In your example picture, you've put the readme MD blob twice, you silly goose. No, I did that on purpose. Again, to remind you that Git stores changes over time, so you might have multiple blobs of the same file because the first blob of readme might be how the file started, and the second blob of readme is a difference, a change, a future revision of it. Ooh, exciting. Remember, we can't cat out the contents of these files because it's nonsense, but we can use git cat file command, which basically does the same thing for us. It gives it back in some sort of useful information. There's two modes of usage, -t for type. So if you give git cat file -t a hash, it'll tell you, oh yes, that's a commit, that's a blob, and that's a tree. Boring. Snoozeville. -p is the cool guy's cat file. If you do -p, it gives you the output in human readable format as you'd expect when you catted the file. So if we give it a commit object, it would look like this. This looks familiar. This is just a commit message and an author and a parent. Every commit has a link to its parent. Dag, yay. And the one that I promised you, every commit has a single tree reference to a tree object representing the root of your repository. Let's take that hash and put it into the same command. We get this output. It's as though we've LS'd a folder. We've got files and subdirectories or blobs and other trees. Nice. Let's take one of the files and stick it into the same command all the way down, and we get finally our plain text code right back to us. Lovely jubbly. Now, if you want to learn more about this, unfortunately, we have very limited time in Detective Academy. However, a very handsome colleague of mine about 2 years ago took a group of enthusiastic cavers into the .git folder cave system, and they recorded their findings. You can find those videos on the droidcon content website or on YouTube's.
Detectives, there's been a horrific crime.
Okay. Oh, hey, students. Sorry, I didn't know you were here. So I know we promised you a mock fake crime scene, but I guess there's nothing better on your first day than a real bloody gruesome crime scene. Just when you go beyond the police barriers, just I'll see you on the other side, okay? Good luck. Unit tests! Oh, God! Who could have done this?
Something so barbaric.
I know, Reffy, it's only a monster. Only a criminal could have butchered these unit tests and leave them on the street for everybody to see. But one thing I do know, Reffy, is with the power that Git gives us, we will bring this criminal to justice. Okay, Reffy, to start with, we need to go back. Somehow we need to go back in time to figure out when the crime occurred.
Hey, dreamer, come back to reality. It's not like we've got access to a time machine.
But actually, Reffy, we do. And it's called Git. Because Git stores changes over time, meaning you can go back to any moment in your repository and recreate the folder structure how it was. There's 3 modes of time traveling I want to tell you about today, and that's 1, just visiting, where you pop back in time, have a little look, and then when you're ready, return to the present. There's do and undo, or take some past change and flip it. Don't laugh, poor Will Smith, he's having a rough time of it. And there's final one, danger mode, which is going back in time, but with a little bit more permanence. We're gonna explain each of these 3 with explanation and then a visual diagram, because I'm an idiot and I learn through visuals better. So, the just visiting time traveling uses the git checkout command. Usually we use that for switching between branches, but checkout can actually take any git ref, and that's basically just a way to refer to a specific commit. For example, it could be a commit hash. It could be a relative reference like head, where I am now, or head -1, and so on. So here's the visualization, our very basic commit history, A to E. We have head, where I'm pointing to now, and if I'm at the tip of a branch, then it says the branch name above it, in this case, main. Along the bottom of the screen, in case you're interested, I have some actual file representations of files that exist in the .git folder. Anyway, here we go. So we're going to use checkout to just have a little look back. I'm going to use git checkout and the commit hash for C, and immediately my head moves. I'm now seeing the repository as though I was in moment C. How exciting, the past. But something else has happened. I'm in something called a detached head state, which is a really weird, terrifying way of basically saying, I'm not at the tip of a branch anymore, Toto, okay? We have a look at the past, and when we're ready, we use git checkout and the branch name to jump back to the present. Easy. Have a little look. There's do and undo, which uses the git revert command. Takes some change that you specify and flips it. The visuals are far better. Again, it takes one ref. Here we go. I'm going to use the git revert command and pass it the commit hash for E. We actually move forward in time. My branch and my head both update, and a new commit's been created. But what's in that commit? I didn't write any code. Well, revert basically takes the mirror opposite of the commit you just told it. So if the diffs for commit E were minus startup, add cleanup, then the diffs for your new commit F is the opposite, add startup, minus cleanup. Nice. And finally, danger mode uses the git reset command. It moves you back in time, but does some changes to your references. And we'll look at what that means in a second. You pick when you want to go back to with a ref, and it has 3 modes of operation, soft, mixed, and hard. And we'll explain each of those, but they basically have a different effect on the changes that you've just abandoned in the future when you go back. Yeah, it's Inception kind of stuff. Here's the visuals. So I want to jump back to C. So I do git reset in soft mode, C. Look what happens. My head changes, so I'm now back in C again, but my branch has updated. Git now believes the top most recent commit of my branch is C. Interesting. The changes from D and E look like they've gone, but those changes from D and E, because I used soft mode, are taken and lovingly placed into the staging area. That's as though I've typed the code, saved it, and have used git add or something to tell Git about their existence. Then mixed, which is the default option. Same thing, jump backs, head updates, branch updates, but the changes from D and E are lovingly placed inside the working directory, as though I've typed the changes, saved them, but have yet to tell Git about them. You've probably guessed the last one, hard, which takes you back as well, but the changes from D and E are lovingly drop-kicked out of existence. But are they? People often say that this is the dangerous command to run, and you should be wary, but it really is not when you understand one of the cruxes of this detective academy, and that's the idea of unreachable commits. Here's what we just had. D and E looked like they were gone, but actually, they're still there. Those changes from D and E, they're still on your machine. They're just not accessible via the usual branch or tagging system. They are unreachable, okay? But for now, asterisks, they're still there. You just can't reach them, right? The changes are there, which means we can bring them back in case we made a mistake. Here's a better visualization of what we're looking at. D and E aren't attached to the usual branching system. So if we want to get E back, we just check it out. Git checkout and the commit hash for E. Again, we're in a detached head state because we're not at the tip of a branch, and we can remedy that by creating a branch from where we are now, and bada bing, bada bip, those changes are back. They've not gone forever. But Detective Kadel, in your example with single characters, it was very easy to figure out which commit to bring back from the dead. What happens when we're using real 40-character long SHA-1 hashes? Well, glad you asked, thank you. The savior command, and one of the greatest commands that ever exist, is the git reflog command. If ever you fuck up in Git, pause, breathe, pause again, and then use git reflog. As you're moving around Git and your references are updating, your head reference, your tip of the branches are updating, Git's keeping a log of that on your machine. And the reflog command dumps that information back out to you. And the most recent entry, top line, is the most recent thing you've done. So if we just did a reset hard, and we're like, how do I figure out which commit I need to get back to? Well, the line beneath it, in the far left column, before you did that reset, we'll have your commit hash. Lovely. Git reflog. But wait. I said those unreachable commits, I'm jumping all over the place, I'm sorry, bear with me. Those commits, those unreachable commits are still there for now until something. Until garbage collection, maybe, right? Git has a very sophisticated garbage collection system, which you can trigger using the git gc command, but it automatically runs on a bunch of different Git moments. Its main objective is to take the current way we've been storing objects, which is in that objects folder, loose, it's called loose because they're just jiggling around in there, and destroying them and getting rid of them, but turning that information into something called a pack file. And now that's where Git really wins the version control wars, but I do not have time to go into pack files, but they are incredible. Again, the cave dive people I talked about earlier, they had a look at it in their videos, check that out. The reason we're looking at garbage collection is because it might, possibly, maybe delete unreachable commits. We'll get to that later. Now, Refi, we've got a little bit of a problem. We've just been randomly jumping back in time, trying to see when the crime happened. We need a better way. Thank you.
Man, this search is gonna take a lifetime. It's like looking for a needle in a haystack.
I know, Refi. It's because we've just been guessing when to go to. We need a tool to help us figure out when to go to. And we have such a tool. It's the incredible Git bisect command. Bisect meaning to cut or divide into 2 bits. It essentially performs a binary search on your ordered Git history for whatever it is you're looking for, right? For us, we're looking for the moment when the unit tests were first brutally destroyed and left on the streets. So, unit tests. How we start it, we use the git bisect start command. And this says to Git, hey Git, shit's about to get weird. We're gonna jump around a lot. You're gonna see lots of weird stuff. Once Git has that, we give it 2 pieces of information. Git bisect good and a ref, and git bisect bad and a commit ref. And these are good, as in the latest moment you know for sure the tests were still working, and bad is the earliest moment you know for sure the tests weren't working anymore. And all that does is it brings that range down to a smaller range to search through. Once Git has that information, it springs into life. It immediately checks out the center commit in that range and then does nothing, because you have to work with it. You need to now tell Git if this is a good or bad commit. So for us, with the test still working, we run our test. Run the test. In this case, the tests were still working. They're good. So we say git bisect good, and Git is immediately able to eliminate this commit and everything to the left of it. It takes the remaining range, checks it out. Again, we run the tests. This time the tests fail. So I do git bisect bad. Git isn't able to eliminate this commit, but it is at least able to eliminate everything to the right of it. Again, it takes the remaining range. We run the test. This time it was git bisect good, and immediately Git stops once the range jumping is finished and says, hey, F. F is the first bad commit. Amazing, F. We use git bisect reset to say, hey, Git, calm the hell down, get out of here, okay? Relax, take me back to the tip of the branch, please, thank you. And we have it, Refi. B99 is our naughty commit when the tests were murdered. And look at this commit message. Made some good changes, ja klar. We should have seen that coming. Best thing about Git, though, is that we can look at all the information. We can use git show with this commit reference and see, for example, the diffs. Oh, God, I'm so sorry. I didn't mean to put that on the screen. That's barbaric. I'm sorry. Well, you've seen it already, but that's the gross moment the unit tests were butchered. Anyway, even better, every commit has an author. So our author, our criminal, is mysterious user at Outlook.com. They have obfuscated their identity.
Curses. Thought we were hot on their tail. It looks like the perp's gonna get away with this.
Well, hang on a second, Refi. I found something here. Look at this. A file called secret.txt that is here in the past, but doesn't exist in the present. The perp has left a clue. Now, cadets, I know it's been a very hard first day for you, but it is tradition at Detective Academy to take a group class photo together to put on the hall walls and for other reasons. So if you don't want to be in the photo, just hide your face. Otherwise, we're going to take a class selfie, make it fun, make it whatever, and unfortunately, you lot are included. But ready? 3, 2, 1. Get my hat out of the way. All right, good. All right, come on, please, calm down. There's been a crime. Misbehaving. Crazy. Okay, Refi, this is interesting. So, like I said, in the present, there's no secret file. But when we check out B99, there's this secret.txt file that doesn't seem that it should still be there. So let's cat it out. Maybe it'll give us a clue. Here it is. Okay, it's just, again, gobbledygook. Right, just send it off to the techies. We'll carry on with our investigation. I don't know.
Hey, partner?
Yeah?
Out of pure curiosity and educational purposes, if the perp had been smarter, how would they have properly disposed of those secrets?
Quite, Refi. It's a strange question, but I think I like your school of thought, because sometimes to catch a criminal, we have to think like a criminal. So yes, let's figure out how we would have properly got rid of those secrets, and then maybe it'll give us a clue to continue our investigation. So the problem that we've got is that at some point in the repository, this secret file was added and committed. And then at some point after that, the file itself was deleted but that change itself was tracked and committed. And remember, Git can recreate your folder structure at any moment in time, so that secret blob is still there in your object database. Not great. The other problem, even worse, is just on the criminal's machine is one thing, but the moment that they push their changes to the cloud, other developers will get the copy of those secrets and the problem propagates. What we need to do is essentially rewrite history. We need to go through every single commit, check if the secret file is there, and if it is, delete it, and overwrite that commit with our own new commit. Okay. We have just the command for the job. It is the intensely terrifying filter branch command. In fact, when you open the man page for filter branch, it immediately goes, oh, warning, warning, plethora of mangled histories, blah, 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 right? And in the wrong hands, filter branch is incredibly dangerous. But we, as professional detectives, will learn how to properly use it so it doesn't scare us anymore. So, I will be upfront about this. If your objective is just secret removal and you just want a boring, easy life, then there's other repositories out there. Git itself even recommends this other tool, Git filter repo, but we're going to skip past that because filter branch. So filter branch, as its main argument, takes a rev list, and that's basically just a range of commits. And by default, it's the branch you're on, hence the name filter branch. Nice. It does some history-altering action that you give it on every single commit in that rev list, not affecting, as you can see in this fabulous diagram, the other branch, the other rev list. Nice. But Detective Kadel, before, when you got rid of blue commits, you've sort of done the same here. Where are those blue commits? And if you're thinking like that, then well done. You're already thinking like a Git detective. Because those blue commits, for now, they're still there, sort of. They're still on your machine. Those changes haven't gone anywhere. We can use the git showref plumbing command, which is an awesome command, lists all of your human-readable references and the commit that they point to. And when we do that, we see something weird. We see this original refs subset. I didn't make that. Git made that for me. In fact, when I used the filter branch command, it backed up my old commits, because although the filter branch is a terrifying command, they're just trying to be good guys. Nobody? Okay. Go watch Rick and Morty, you heathens. What about the garbage collector? If we ran the garbage collector now, because of that pointer to those original refs that backed up, they're protected. They won't be destroyed, okay? They're not technically unreachable. We can even use that reference to check out our old changes and have them back. Ah, nice. All up until something deletes that reference. And now if we were to use the garbage collector, it would eviscerate those old commits and clean them up for us. Okay, so back to filter branch. It takes one or more filters, and filters are weird. There's so many filters. I'll let you look at those in your own time, but we're gonna look at two, because one of them, message filter, is super easy and will help us understand this command. An index filter is the useful one. So, a filter basically lets you put a command and affect a very small area of history, a very small area of history. So message filter just affects the commit messages. That's it, nothing else, commit messages. You give it a command, and whatever command is run on every commit message, okay? Let's have a look at some examples, because that is confusing. If I use the message filter, and then in the quotes after it is the command I want to run on that filter, I just want to echo out glory to Super Earth. So all my commit messages will now look like glory to Super Earth. Now, I'm not entirely sure why you do that. Probably because you're a good democratic patriot. Hold it. Hold it. Glory to Super Earth, am I right? Fuck. Yeah, that game kind of fell out of... Anyway, it doesn't matter. Good, back to work. How about a more useful example? Remember, filter message, as its standard input, takes the original commit message. And whatever you print out to standard output is the new message. So you can string manipulate the incoming message, and in this case, I've wrapped hyphens around it. Boring. Or you could base64 encode your original commit messages, and it looks something like this. Kind of looks familiar. Anyway, moving on. So before we've run the filter branch with the message filter, we have our list of commits. After we've done it, we've got duplications of all of those commits. And what's important is the author for those commits stays the same. We do not want to affect any other scope of history, just the commit messages, that's it. And even more importantly, those commits still point to the same tree object they did before, because we've not changed anything else. Okay. Over to index filter, the useful one. This scope of history that it affects is the index, or the files that Git knows about in that moment. You can always query that information with the ls files plumbing command. Let's look at some examples. We could do index filter and the command after it, git add, and another file on my machine. And that would make it as though that file had always existed, silly. You just weren't paying enough attention. It was always there. Or the more useful one, which is git rm, to remove the file. And that would make it as though the file had never been there. You didn't see anything. And squat. Oh, I'm getting old. So this terrifying bit of code is a single-lined secret removal command that you can copy and paste, split over to multiple lines. It looks terrifying, but we're going to understand each and every part of it, because it's not. We can use one or more filters in the filter branch command. Here we're using two. Each filter in red has its command that it's manipulating on the left. And we've seen the first one already, index filter. So git rm with some flags. In fact, the ignore unmatch flag is really important here, because if you run git rm on a file that doesn't exist, Git will complain. But if you put ignore unmatched and it can't find the file, it'll be like, I tried, carrying on. Because maybe that secret file was not always there throughout history. Oh, yeah, interesting. There's tag name filter, and the scope of area that it affects is the tag names, like version 1, version 3, version nod. And all this is doing, cat is taking a standard input, the original tag name, and spitting it right back out. We don't want to change the tag names, but what we want to do is make sure the tags are pointing to the right new commit that might have changed now. Interesting. The filter branch command itself has some options. Prune empty is amazing, because if the original commit was just adding the secret, and now the secret's gone and that commit's empty, then we don't want that commit. Just get rid of it. Gone. Force, again, is amazing because it shows us that filter branch is trying to protect us from ourselves. If without this flag, force, if we run filter branch and it can see that we've already got original refs backed up, like I showed you before, it'll be like, no, bro, no, you're on your own, good luck. But with this force tag, you're saying, yo, I'm crazy. Do it. Overwrite them. I know what I'm doing. Dash dash is a Unixy thing that says that's the end of the options, and then dash dash all is a rev list nickname to say all branches, all tags. So we are affecting all branches, all tags. Now that is the command. If you run it and you're like, oh, I'm not sure if I should have run that, then don't panic. There's still time. Like genuinely, there's still time. When you hit enter, that command puts up a message but doesn't do anything for the first 5 seconds. It just sort of looks at you like, you didn't mean to do this, did you? And look, it even recommends that other repository I was talking about. Good old Git. Alternatively, if you've passed 5 seconds and it's running and you're like, oh, I'm going to get fired, then please don't panic. Because remember, those changes that you think are gone are backed up in your original refs. Easy peasy. The last problem, and unfortunately there's no way around this, is those other criminals, other developers out in the world. They have those secret blobs. And the only answer to this is you need to force push. You should never force push. But in this case, you need to force push. And you need to force push all the branches, all the tags. And the only bit of advice I can give you here, try and avoid it. But if you can't, do it with your team. Get in a call with them or get them all in a meeting room and let them see you hit the enter button and let them watch and laugh as you panic and sweat.
Detectives! It was base 64 encoded.
Revy, base 64, of course it was. I knew I recognized that format. We can decode base 64. Here we go. Let's decode it and see if there's any more information for us. It was me. There's plain text. We've got a confession, Revy. It was me, your partner. Revy?
I'm sorry, partner. It was either me or you. I didn't have a choice. He told me he'd revert my child commits if I didn't do what he said.
Revy, how could you do this to me, buddy? We've been friends for years. You should have spoken to me. Who even is this guy?
All I know is he goes by KB. He looked just like you, but with a mustache.
Revy, I'm not going to make it, buddy. You got to help me, Revy, please, Revy.
I gotta go. I'm sorry.
Revy, no. Awesome. Thank you very much. please, no, stop. No, thank you very much for coming to my ridiculous talk. I hope you had fun. I know I did. Again, if you want to learn anything about what I just said very briefly, there's loads more information in the link tree provided there. There's my stupid socials on screen. And I am one of those assholes that has my very own branded merch with me. So if you like my stupid face, then I have a Ben Kadel sticker. I have a Ken Bedell sticker. I have this year's very limited edition Refi sticker. There's only a few of those in the world. And I have my Ben Kadel pins. So if you want any of that shit, then meet me here, or just sort of like bum rush me when I get off the stage. Thank you very much. Have a great rest of DroidCon London.